every time you run XMapTools, it will end up with this window saying you have to pick up a working directory. The idea is when you open the program, you pick a working directory, XMapTools is going to generate a lot of files. And so everything will be generated automatically in this working directory. In my case, I'm simply using this tutorial EPMA 2023. This is the folder on my desktop, and I'm simply going to open that directory. And so I click open. What do we have in this directory? We have those X-ray maps, and they are in a compatible XMapTools format. If you are using a microprobe, a geol or Cameca, you will not obtain the data like this. But I have an import tool here, a data conversion tool for EPMA. And if you press that button, it will open a small interface where you will be able to read the raw data from your instrument. And what the program will do is generate this data in the right format. And we have for each element one file. It's a simple text file. There is no header. And if I open one, for example, titanium.txt, what you see is the intensity of titanium for every pixel. So it's simply a matrix. And what you see is already a map somehow. Huh? If I go a bit down and you see that we have increasing counts for titanium. So what you see on this image is simply what we will then visualize with the map. There is another file that is important. This is called standards.txt. It has been generated by XMapTools during the data conversion. It contains the coordinates of your map. This is the first block. It contains the elements that you measured with your spot analysis. And those are the different measurements that are corresponding to the area of your map. So those are only the measurements in your session that were on this specific area. And again, you don't have to label your measurements to say where they were measured. The program will read the coordinates and calculate everything for you. From the microprobe data exported to this, it takes about 1 to 2 minutes. And then you can start here. Okay, the first step is to import the maps. So I simply press here the button import. And so you open the import tools, you can select the files that are in this working directory. You can select all files. XMapTools will find out what is a map and what is not a map. The elements will be detected automatically based on the name of your file. For example, calcium.txt will be interpreted by XMapTools as a map of calcium, probably measured with WDS. The underscore here, before the name for phosphorus, nickel, and other, is simply to indicate to the program that this map was measured by EDS and not WDS, because there is a slight different procedure for importing data from EDS to WDS. You simply select all the files and you press the button open. And XMapTools will load now the maps. Might take a bit of time. And once all the files have been imported, it will list here in this table the different files. This is the first column, the type of map it is. It has detected the elements for the different element maps. For secondary electron image and topo, it says, no, this is other, this is not an element. This is the name of the map as it will appear in XMapTools. And you see now that the underscore for the EDS is not anymore there. So this map will be indexed as a Cerium map. The category, it will go to intensity data. So XMapTools thinks that this is intensity data. If, for example, you are using already calibrated data, you can click on that and change it from intensity to weight %. So this is something you can change. The special is for me to detect what is EDS, what is WDS. And the reason for that is there is dead time correction for the WDS spectrometer. So the wavelength dispersive spectrometer, and the program will apply a dead time correction in this case. The destination is where the data will be sent in XMapTools. You can also edit that, and the action is simply to keep all the maps. In this case, we're going to keep all the maps. We're going to go to the tab corrections, and we're going to simply change the dwell time because I used to measure this data set a dwell time of 100 milliseconds. And this is what is used to do this dead time correction for every pixel intensity. The idea behind that is that when you measure an X-ray intensity, you have a time during which the detector cannot measure a new photon that is entering the detector. And this is what we call the dead time. And there is a mathematical expression to correct for this data. So once we have changed the dwell time, we can simply click import maps. So far, I opened the program, I pressed the button import, and I imported the maps. And you see that the maps are listed in this primary tree menu. You can select here one element to display the corresponding map. You go through the intensity. So we are in the category intensity data. And then we can simply go through and display the different intensities and the different minerals. So something I want to show you here is about playing with the range of data that you display. Most of the time, here the maps look very nice because when you select a map, for example, aluminum, XMapTools will pick the minimum value of your data set for aluminum, the maximum value, and it will apply here the color scale across between those two values, the minimum and the maximum values. And this is represented on the small absolute frequency polygon diagram. It's like an histogram, but instead of showing the bars, you simply connect the different dots. And it shows the distribution of the pixels with the different intensities. There are no axes, and the y-axis is log. So the peaks here correspond to the different minerals. And you see that you have three different bars, the red bars that shows you the minimum and the maximum values. And that's the one you can simply click on the bar and change it to adjust the range of the data that you want to plot. And in this case, everything that is below this value of 510 counts will be displayed in black. What you can do, for example, we can also change here the upper value, focus on those two peaks. So now we should have only two minerals that are displayed using this color range. And for the lower value, I have this black layer, but for the upper value, I'm not putting any layer. Every pixel shown in red, in this red color, is equal or above the maximum value. And this is a very important decision. I want to show you this because it is important that when you show in your publication, in your presentation, a map like that, we have no idea what the intensity or the composition or whatever the unit is of the pixel in red would be. We simply know that they are equal or above the maximum value. If you want to get rid of that, you can simply go to options. And here we have some options for the color bar. You see that we have the lower filter. This is the black color that is there. And you can decide to simply apply an upper filter as well. And all those red pixels would now disappear. And only the pixels between this range are shown. But by default, XMapTools won't do that. And you can also decide if you want to change the color. You could use white, for example. And those are settings that will be saved in XMapTools. So if you adjust the settings, they will be saved in your project. We have also different color maps, and those are the different color maps of XMapTools. They are taken from the literature. You have also those SCM, those are the scientific color maps that were published a few years ago. If you simply select one, it will adjust the color map. So if you don't like my default color map, no problem. You can change the color map in this menu. You can also use a log scale for the color scale here. This is quite important when you work with trace elements. You can invert the color map if you want as well. You can adjust the minimum and the maximum values by using those sliders. You can also change the values here. And what I have developed is an algorithm that can do that for you. If, for example, we select here manganese, we can click on this button. It's called Auto Color Contrast, and it will simply try to adjust the color contrast. It doesn't work very well when we have a map for all the minerals, but you will see that when we have single minerals maps, then it works very nicely to click this Auto Contrast button to adjust automatically the contrast. I'm always clicking on the map at the auto contrast button to really enhance the contrast, see what I have. And then if you click a second time, it will improve again the contrast. If you click a third time, it will restore the original min and max values. So this is quite straightforward. To select a map, click this button 1, 2, and 3 times to come back to the original min and max. So this is how you can play a bit with the program to adjust the color limits, to visualize your data. And we can already visualize some compositional zoning in the minerals here if we select this garnet here, but we will come back to that. With iron, you see that now we start to see some zonation. So it's all about what you select. the range of the data that you want to visualize. When you start with a data set, you should recognize the different minerals that you have in this sample. And here I can easily show you the different minerals. We were on iron. Iron-rich mineral in this case is a garnet. We are looking at a sample. It's a metapelite, so it's a metasediment. And we see so garnet with potassium. We will see biotite growing around the garnet and in the main foliation. We have an aluminium. We can see some sillimanite. This is high temperature metamorphic mineral. We have also some chloride here in yellow that comes probably after cordiorite. And if I look at silicon, then I have quartz, and we have some plagioclase. Let's look at calcium. Yes, this would be some plagioclase in red here. So it's a quite simple rock with a simple mineralogy. The idea is to show you how to classify this. How can we separate now the different pixels into the different groups of mineral? But the first thing I usually do when I start a new project is that I eliminate the maps that I'm not going to use. And in this tutorial, for example, we are not going to use cerium. Cerium here was measured with EDS. And the only important thing for cerium is this red point is in the middle, that is a monazite. And apart from this monazite, all the variations that you see are variations in the background intensity. So the variation you see are not related to composition. I won't keep the cerium. If you want to eliminate a map, you simply select it in the menu, right-click, and then you press the button delete. And I'm going to eliminate also chromium in this example. I'm going to eliminate nickel, and I'm going to eliminate sulfur. I'm keeping lanthanum because of this monazite crystal, just in case I want to classify the monazite. And I'm keeping the phosphorus also for this monazite. We are not going to classify those accessory minerals in this example. A very important aspect is once you have loaded your data and eliminated a few maps, it is quite important to save your project. In XMapTools, you can always press the save button here. It will open the window and say, do you want to save your project? It will be saved as a MATLAB file, a MAT file. And if you open it in MATLAB, you can have access to all your maps, all your data which are saved in this project. And here I'm just going to keep the name, click save, and the program will save this project. Now let's move on to the classification. And so the idea is to create this classified image where each pixel is allocated, is distributed between the different minerals. So it could be minerals, it could be glass, epoxy, whatever feature you want to classify on your image. So in XMapTools, the classification is what I call semi-supervised, because I want you to have the full control on the classification. The idea is not to give you an algorithm that is able to identify the different minerals for you. That would be quite terrible in my opinion. The idea is you should know before you map your sample what minerals you have in your specimen, and then you want to be able to do your classification in XMapTools. Everything for the classification is in the second workspace here that is called classify. What we're going to do is first create a training set, and the training set will be pixels that we know to which phase they belong. And the training set will be stored here in the secondary tree menu, that is here, training sets for classification. You select this training set for classification, and when you select this one, the button add here will become available. And this button is simply to add a new training set. So I click on the button, add a new training set. And now the program will open a window to let me select different phases that I want to include in my training set. So in this list, I'm going to select, in this case, biotite. Then I'm going to select garnet. I just hold the command keyboard to select more phases. Then I have this plagioclase here. Where is plagioclase? Then I select quartz. And in this case, I'm going to click apply. But you see, you have a list of the common rock-forming minerals, and you have also some generic names if you want to call it phase 1, 2, 3, order. It's quite used, it's quite important. And then I have a full database of mineral names. You should find your mineral in this list. And then I simply press apply in this case. So I have selected 4 minerals. And you see now they appear just below. We have this biotite, garnet, plagioclase, and quartz. We want to define some training pixels for biotite. We need to be able to select pixels for biotite. And for that, I'm going to select potassium. I'm going to zoom on the image. So I'm clicking the plus button and then I'm selecting an area. So I just activate the zoom, then I select an area and I can zoom over this area. Okay, so the biotite pixels are now in yellow. Those are the ones rich in potassium, and I know that everything here is biotite. So I select biotite in the secondary tree menu. I select the shape of the region of interest that I want to use. So let's, for example, start with rectangle, and I click the button add. And now XMapTools is expecting me to draw a region of interest to select the pixels for biotite. So I'm simply clicking, holding the button, the left button, and then releasing to define this region of interest. In my training set for biotite, I have this rectangular region of interest, that is this one, that contains all the pixels inside. We can add a second one, let's say, for example, just to show you to use a polygon. So if you want a more complex shape, you can simply go here and then you can click on the different parts of the grain to define your polygon. And then you simply click on the first point to close the polygon. If you are not happy with your selection, you can always select here the object in the secondary tree menu, and you can change, you see, the selection later on. So you can adjust the selection later on by selecting the object. If you are not happy with one of them, you can also right click and click delete, and that will eliminate the region of interest. What we need to do is to define region of interest for the main minerals that we have in this list. So I have already done biotite. Let's go for garnet. So we can change the view to go to garnet. We can also restore the view. Here I'm selecting garnet. I'll keep the rectangular region of interest, click add, and simply select a few pixels here for garnet. You have seen that we have a minor compositional zoning between core and rims. Maybe I'm going to select several areas for garnet. Let's say here, and maybe one at the rim. So you can do that very carefully. The good thing with this classification method is what you teach to the algorithm will be applied. So you can really tune the classification by carefully selecting the region of interest for your mineral. It's just a few tens to hundreds of pixels for each class would be enough for the algorithm to do a good job. Now I can go to plagioclase, simply display an element where I see the plagioclase, let's say sodium, click add, and select a few pixels for plagioclase. In this region, then we go quartz, silicon, and I select a few pixels for quartz. And so this is how you create your training set. Now at the moment, I'm missing one phase, that is the chloride. I've been replacing the cordierite. So I'm gonna simply go on the phase definition again, click add to add a new phase inside. So let's go to chloride, then click apply. And now we have this new chloride class. I'm going to go to aluminum, add, and then I can add a few pixels for the chloride up there. Very good. And we are still missing one phase that I forgot to add, that is the sillimanite here in red. So I'm going to click add. And I take the sillimanite, I'm zooming on the image. So you see the sillimanite is a bit more complex in this example because it's mixing with quartz. You have all those yellow pixels that are mixing pixels with quartz. But here I'm gonna just take a group that is quite large, and I'm gonna take some of those pixels with it to say, okay, I want the mixing pixels to go with the sillimanite phase. Okay, that's my definition for sillimanite. So now the training set is finished. And you have to select here in the second block, those classification parameters, you have to select the different maps that you want to use to perform the classification. As the algorithm is quite good, what we can simply do is press that button to add all maps. So if you select one intensity map and you press that button, this will add all the intensity map. But if you are working with already quantified data, you can simply select one of these data, click all, and it will add all the maps for classification. If you want to exclude some of them, for example, if we want to exclude lanthanum, because it wouldn't help in this case for the classification, we select lanthanum, we click take lanthanum EDS out, and then it will exclude it from the list. So those are the elements that are selected for classification. Then you have several options. We are just writing at the moment the paper that will describe all the possible options. The idea, you can use the maps, you can use some principal component analysis, so you can transform the maps as well. And we have some textual analysis that is possible. There is the option to scale the data, and here we are using a given equation for the scaling. In the random forest, there is a random component, so I have a reproducibility option. That means that if you activate that option, you will always get the same classification with a given input. And the option here will be the maximum number of trees that we will have in this random forest. So when you are ready, you have to select a training set to activate the classify button. This is important. The classify button will only if you have a training set that is selected in the secondary tree menu. And when you are ready, you simply press the button classify. And so the program will take all the maps listed here, train a random forest, and this is already done in this example, and then we'll classify all the pixels. And what you see on the two figures here are the number of grown trees with the out-of-back classification errors. And this is a very simple classification task, which means that for usually 15 to 25 trees, the classification error should go to somewhere close to 0. The second figure that you obtain is this predictor important estimate. And that shows you how much the map is important for the classification task. For example, if you have a map like phosphorus EDS, that is with a very low predictor importance, what it means is that if you exclude phosphorus and you redo the classification, you will obtain a similar result. And after the classification, you obtain the third figure here that shows you the number of pixels that you selected for each class, and that will be the true class on the y-axis. And on the x-axis will be shown the predicted class. And what you see here is simply all the pixels I selected for biotite were classified at the end as a biotite. And this is quite important to check, because if you make a mistake, for example, if you select one phase and you divide it between two classes, the algorithm will struggle, and you will realize by looking at this figure that something is not working. So this is one way to check the quality of your classification. What is very important to remember is as you create your training set, you could, for example, say to the program, classify biotite and chloride together as one class. The algorithm will simply do it for you. And the result you obtain here is a mineral distribution map that shows you with each color the different minerals. And what I have implemented in this new version, all the minerals have a specific color, and we have a database of colors for the rock-forming minerals, which means that you will now be able to automatically compare all the maps. So if you have a sample with 5 different maps, all the minerals will have the same color on all the maps. So this is much easier for you compared to if you have to change the color by yourself. Of course, if you don't like the color, there will be also an option to adjust that color. And here there is an option that you can edit the colors for the different minerals manually. If you don't like the color that is automatically attributed to your mineral, you can simply double click here and it will change the color. So you can pick a new color if you like. For example, here I'm going to just do something to change it to show you. Now I have changed the color of quartz to pink, but this is really bad. So I'm going to reset to the original color. And then I can apply the changes and come back to XMapTools and everything will be saved. That was to show you the classification. I'm going to quickly save my project. And now the goal is to check the results of the classification. So to check if we have done a good job for this classification. And the idea is simply to look at the different classes that we created that are now available in this mask file. And you see that in mask files, you have a first mask file that has been created that is called random forest maps. The name is based on the data you use to classify. And now if you select an intensity, for example, silicon, and you select biotite, only the pixels of biotite will be plotted by the program. And there you can see if, for example, you would have a second mineral that would be selected, you will be able to identify that there is a problem and you will be able to adjust the training set and recalculate a new classification. So I'm going to quickly check my garnet. You see that I have some pixels here that are clearly not garnet and they were classified as garnet. For example, this accessory mineral, the monazite, was classified by the algorithm as garnet. And this is normal because I didn't train to recognize monazite, but I could go back, add a new class in my training set, select pixels for monazite, and redo the classification. When I said that you have the full flexibility to classify your data, and it's very powerful, it's because of that. You can really do it the way you want. Plagioclase is pretty good. Quartz is really good in this case. I have some pixels here in blue. This means that maybe I have something else I should look at carefully if I'm interested in that. Chloride, we get some mixing pixels. You see all the blue here and the red are mixing pixels. And this is something probably I could improve by spending more time in the selection of the pixel. I'm going to leave it like that for this example. Chloride was taken as when you are close to sillimanite. And this makes sense because those are the minerals with the highest aluminum content in this sample. And aluminum was one of the important elements for this classification. For this one, I would say it's enough, but you can check if all the pixels are well allocated. You can check, for example, several elements. Of course, yeah, I only use silicon, but you could use, for example, aluminum, or look at elements that are not in your face, for example, iron in plagioclase, and you see, oh, we have some mixing pixels. By mixing pixels, I mean a pixel that has a composition that is between two different classes. I'll come back and probably later show you how we can identify mixing pixels in another way. When you are happy, you just save your project and say, okay, now we're going to work with this mask file. If you change something and you want to change the algorithm, which is very quick, is you can simply go back to this training set, use another algorithm. We have several algorithms: discriminant analysis, naive Bayes, support vector machine, a simple classification tree. We have k nearest neighbor and the k-means. And you can simply pick another algorithm, classify, and the program will perform a new classification task. And here in this case, you see that we have now two mask files. We have one for the random forest here and one for the discriminant analysis. And when I go from one to the other, you see that at the end, the differences are quite minor, but they will mostly be here in the amount of mixing pixels. So the discriminant analysis will handle the mixing pixels in a slightly different way. You can also eliminate mask file by selecting them and clicking delete here, right click on them. So you select, then right click and then delete. Now I'll show you how we can extract mineral modes. So how we can extract the abundance of our minerals from this mask file. So for that, we have to display the mask image. And to display the mask image, we always select here the mask file in the menu, and it will do this plot. And on the right here, you see that we have this mask analysis and visualization. And this will allow you to extract the modes. And the very simple way is to use the rectangle region of interest. And then you can click the button Add Region of Interest, drag over an area to select the area, and the program will generate the surface percentage of all the pixels of the different classes in this area. And it will also show you the number of pixels of each class. And this is the pie diagram showing the distribution of the modes. And if you want to save that figure, put the pointer over the figure, click here, and then you can save or copy the data. Okay, if I change now this region of interest, the modes will automatically be adjusted. So this is quite convenient because you can really go from the full map to a simple domain of your map. For example, in my case, that part, and you could extract the modes for different regions of your sample. Okay, if you want also to save those data, what you can do is you can copy the data to the clipboard. If you simply click on that button, it will copy this data. And if you paste into Excel, for example, or into a text file, then you will get a nice table with this format. And you can also decide to save it, save data as a text file. I'm going to press this button, save, and just say, okay, this is the modes for retrogression, and simply click the button, save. Now, if we navigate to this folder, you see that we have in the working directory, we have now a folder that is called exported mode, and we have the text file inside. If I open the text file, you get the data that we exported, the date of today, the type, the mask, the mode, and the number of pixels. So it's quite easy to export your data. And you see, that's why at the beginning, the working directory was so important, because it has exported directly the data at the right place. Every time I have a given project, a set of maps, it will be one folder on my computer, and I'm always working into that folder. This is for the modes. Once you are done, you can eliminate the region of interest here by clicking Reset the ROI. You can use a more complex polygon region if you like, if you want to do something a bit more fancy here. Select a region and it will export again. It will generate the modes. and give you the numbers here. And when you are done, we can simply reset here the region of interest. Something I also integrated in this version of the program is the point counting. You can say, I want to generate randomly 900 points, and it will calculate it for you and extract the modes using that method. So you can decide here the number of points you want. And this idea was just to compare the approach of using X-ray maps in this case, compared to the point counting approach, because 900 points would be usually quite good to estimate the modes. And if I calculate here the pseudo modes using this point counting method and I save it, 900, for example. And if now I want to compare that with the rectangle and the modes for the same area, I could compare the results. So I'm going to just do it live and then go to my data. I save this point counting. What you see is the biotite was 15% in the point counting, 16.79, 7% of garnet, 6, 29 of pyroclase here was 28.7, 37 of quartz. You see the difference, and you have quite some variability, especially that if you redo the point counting again, you will get slightly different results because every time the coordinates will be randomly determined. So this was the idea to show you what you get with this point counting method. I even implemented an uncertainty calculation using Monte Carlo, so you could repeat that sampling technique 1,000 times automatically. That will calculate what is the precision on your point counting. And when you do that, it would be the equivalent of selecting 900,000 pixels on your image. So that will give you a quite good estimate of the different modes. But you can test it if you want. You simply click that option, press calculate pseudo modes using point counting, and it will take a bit longer because of this Monte Carlo simulation. We have done the classification. That was the first step. And then the second step was the calibration. And again, it happens in this workspace. So we're going to switch to the next workspace, that is the calibrate workspace. I'm going simply to display a map, for example, aluminum intensity. Now we're going to import the spot analysis that I had in this file, standardization.txt. So we simply press that button and the program will detect the file standards.txt and will import it directly. What you see now on the figure is still this aluminum map, and on top of it, every pink dot is one of the spot analyses that I measured on the same area. And there is a label. The label here is shown in white. You can change the color of the label here by going on the resolution. Here you can change the color of the scale bar, and you can also, this will also change the color of the labels of the spot analysis. When you import the spot analysis, XMapTools will have access to your map coordinates and therefore will be able to determine the resolution of your pixel on this image. 1 pixel has a resolution of 20 micron, so it's a quite large area, and you can decide to add a scale bar, and this will simply add a scale bar in the bottom left corner of your image. Here it would be a bit better to put it in white, and now we have the scale bar in white and bottom left corner. But I'm not going to show the scale bar here. It's just when I want to export the images, I'm happy to have a scale bar on the final images. So let's go back to this calibration and the spot analysis. So all those spots, they are listed here in the secondary tree menu as spot number 1 to spot number 106. So we have 106 spot analyses in this case that were imported. So those are the ones that were listed in this file standards.txt. You can select one of them or any of them, and that will show you only that spot. And so this is the first spot here, located here. And on the right side, it shows you the composition of that spot analysis here in oxide weight %. And on the left, what you see is the corresponding intensity of the pixel underneath the spot. So this is what is used to calculate this calibration curve. And then you have the coordinates, the original coordinates on the map. Those are simply the pixel coordinates on the image. And you can, if you want, decide to move the spot. So if you have a spot that was slightly different, or because the sample is slightly moved during the spot analysis measurement and mapping, this could happen. You can simply correct here the position by moving the spot. And you can go through the spots and you see now where they are. You see the composition, and if one is bad, you can simply right-click on it and delete, and that will eliminate that specific spot. When I click on standards, all spots, you see that we have this figure on the right, and the figure is slightly different. And now the idea is the program is taking all the spot analysis as a single profile. And this is what is plotted here on the small diagram on the top right. So on the x-axis, you have the number of the spot analysis. So let's say the point number. And on the y-axis, you will have in blue the intensity data from the pixels underneath each spot. And in orange, you will have the weight % composition of the corresponding spot analysis. The two profiles should be quite parallel if the location of the spot analysis is quite good. And this is exactly what this allows you to check. And indeed, what the program is doing here, it's calculating the correlation between the intensity and the weight % data. So it's calculating the correlation between those two curves. And this is the result that is plotted on this map. So in the center position, the value of the pixel here in the center, the correlation, and you see it's the maximum value here, it's around 0.9. So it's a very good correlation. And this is the correlation between the two curves on this figure. So what this figure is showing you is what would happen if you would move now the spots. So if you move, for example, the spots of 3 pixels to the left and then 3 pixels up, then the correlation between the two profiles will be different, and that would be the correlation. This is the correlation for one element, aluminium. This is the correlation for the sum of, it's the square root of the sum of all the squares of the correlation coefficient for all elements. So that shows you the best position for your spot analysis on your map. And this is important because here it works. You see that there is a very good match. The position of the profile corresponds to the highest correlation for several elements. But sometimes it can happen that there is a small mismatch. And in this case, you can simply select the point here, move it over the area, and that will move all the spot analysis. And you see it now, they have all moved off about, let's say, 9 pixels to the left and 8 pixels to the top. And this is this shift. And if you press that button, that will apply this modification. So now the program will recalculate all the profiles now moved to this new position. So the spots have been moved all together. And here we see that it's pretty bad. This is not something to do because now the correlation for calcium is really terrible. And it would be the same if we go for any element. You see that now we have clearly a mismatch between the intensity data and the weight % data. So I'm going to move back to the position here. It was about here. If you are not exactly back at the right position, what you can simply do is click again the button import, and it will re-import the spot analysis. So it will redo the job and go back to the original positions. And this is where we have the perfect match between the spot analysis and or the weight % of the spot analysis and the intensity data. What you can also do is you can add your own spot directly on this image. So if I select the standards and I click here on the button add, I can simply select now a pixel, for example, at that position, and that will create in that menu a manual spot number 107. And here you can enter the composition in oxide weight %. So here I'm entering just to show you as an example, a composition for quartz. So I know quartz is a 100% silica. And for this position, now I will have a new spot for quartz. And if I move away, I select another spot and come back to this one, you see that the 100% is now reported in green, which means that you have edited that value. And this is the value that will be used for the calibration of quartz. And I'm going to simply add another one, select another pixel for quartz, and I add again 100%. So you could enter manually spot analysis and XMapTools for each of your phase by using this technique. Okay, so now we have all those spot analysis. And in the previous version of XMapTools, it was very important to check the quality of each spot analysis before to run the calibration. In this new version, you can really take everything together and the program will figure out what is good, what is not good, and do the calibration almost automatically for you. So what you need to have to run the calibration is to have those spot analysis, to have your X-ray maps, and then you need to select a mask file because there are different matrix effects between the different minerals. So those calibration curves, they will have different slopes. And if you select a mask file, then the button calibrate here will become available, and this will open a calibration assistant for EPMA data. So now I'm going to click here, calibrate, and the program is running the calibration for you. It's a big black box. The program does several steps of optimization to try to find the best calibration curve for all the minerals and all the elements. And once you get that calibration assistant for EPMA data, the calibration has been done for all the minerals. And it is a new implementation in XMapTools 4, and it follows the strategy we published a few years ago in 2019, but now it's fully automatized and it's working quite nicely. So the idea is the program does first a general fit, and the general fit is to say, okay, let's forget about the matrix effect and try to fit a curve through all the spot analysis we have for the entire map. So if I select, for example, silicon here, what you see is now the fit between all the spot analysis. On the x-axis, I have silicon weight percent. On the y-axis, I have intensity. And that will be my general fit. This is the dashed line here. And of course, you see it doesn't work. Some of them are on the line, but some of them, like the quartz, are quite off the line, which means that if you would transform your map directly from intensity, the silicon map, to silica, the quartz will give you a total in this example of about 110 to 115 weight percent, because it will be off the calibration curve. Those are the matrix effect. And this is why we need to have one of these calibration curves for each mineral. For XMapTools, it is quite important to have this general fit because it gives you an anchor, and then the program can search around for every phase to search what would be the optimal fit. So this is why it does first this general fit for all the elements. And then if you go now to biotite, this will be the calibration curve dedicated to biotite. And now this is the black line on this diagram. This is the final calibration curve. And on the dashed line is this general fit that I showed you just before. And you see it's slightly off, but this is important. If you want a precise calibration, you need to take into account that difference. What do we have below? On the left, we have the silica map in oxide weight percent. And on the right, we have the total map in oxide weight percent. And this is just to give you an idea of how good the calibration would be. It allows you to see if you really get something, if you have a weird calibration. Then the table on the right is indicative to tell you a bit what's happening. So if we take, for example, silicon, there was 30 spot analysis for biotite that were used. This is the median intensity of all the pixels of biotite. And this is the median weight percent of all the spot analysis. And that would be the peak weight percent of all the pixels. So this is a bit complicated to read this table because those numbers sometimes are slightly different, but that makes sense because we are looking at the median of all the spot analysis. And here we are looking at the peak, this more likely value for all the pixels. And depending on if you have, for example, a bad analysis here, or if you have a peak shape that is a bit different because you didn't measure all the composition, those values can be slightly different. So what is very important is to see that here we reproduce all the spot analysis that go through this calibration curve. And usually the total is quite a good indication that the program is doing a good job because you can have substitutions in your minerals. So you can have, for example, a bit lower iron and a higher magnesium, but at the end, the total would be okay. So here you can simply go and display the different calibration curves. So this is sodium. For example, I'm looking at calcium here, and that tells you if the program has done a decent job. What I recommend is to really go through each of those calibration curves and to make sure that you agree that the program has done something that is reasonable. This is your responsibility to check that the results are good. It's working well most of the time, and I'm trying to improve when it fails. And so if you have a case that is failing, also you can send me that and I will try to improve the algorithm. And this is a nice example of iron to show you the problem. We have compositional zoning in iron between about 10 weight percent and 14 weight percent in our biotite. And what you see is that the calibration curve is going through all the points. So it's doing a decent job for the calibration of iron. Same here for magnesium, and maybe one even more important, that is titanium. We have a quite significant variation in titanium. We have one outlier. The program plotted that dot in red because it detected that this is an outlier. And you see that the calibration curve is doing a decent job in this case. You can go through the different minerals, check the different elements. I'm not going to do it in the tutorial. I'm going to just accept the calibration as it is. But I really encourage you to check carefully the calibration of the different minerals. There is one thing I can maybe add, is that if the calibration is not good, let's go for this example of manganese in plagioclase. So I should have no manganese in my plagioclase. And indeed, I have very, very, very small numbers in a few spot analysis. And so the calibration curve is taken as the black curve here. What you can do, if you think that this function is not doing a good job, you can use this adjust manual button here. I have this background value here, that is the intercept, and I have the slope. So I could, for example, modify the slope from 268 to 300, and that will change the curve here on that figure. But here you don't see the difference. It's very close, similar to the previous one, but you can adjust that curve manually to fit your data better if the automatic algorithm hasn't done a good job. But otherwise, if you're happy with the calibration, you can simply press apply standardization, apply to all masks, and this will calibrate now all the pixels of the image. So now in the primary treatment, you see that we have new data types. We have data types in quanti. So those are the individual maps expressed in oxide weight % for the different minerals. I'm going to quickly save the project. And now we are looking at fully quantitative compositional map. This is silica in biotype. Let's go for an element with zoning, for example, iron oxide. I click the auto contrast, and now you see the zonation, and we are fully quantitative in weight %. You can do it for all minerals. And now you understand why the auto contrast button is so important, because when you select one of these elements and it takes the min and max values, you do auto contrast and you immediately get a quite nice overview of the zoning. So those are the individual mineral maps. In the next category, merge, what you obtain here is a fully quantitative compositional map expressed here in oxide weight %. From that, we can use this to obtain what I call local bulk composition. That would be the bulk composition of a local domain in your rock. So to generate the local bulk composition, what we need, because what we have on this image is for every pixel a weight %. And then what we know is the surface of our pixel. If we want to calculate a bulk composition, we need to know the surface % of the minerals, the composition of each pixel, and by assuming that we know volume, try to calculate this bulk composition. But if you want to use the weight % of the oxides to get the bulk value, you would need to correct, so to go from the volume fraction of the minerals to the weight fraction of the mineral, because you need to have a weight fraction. And for that, you need to assume the densities of your minerals. So what we need to do is to generate a density map. And in XMapTools, if you have igneous or metamorphic rocks, you will have the density, the average density of all minerals will be included in the program. So if you select the random forest map, then I have to go back to this calibrate, and you click this density, generate a density map. Then the program will automatically allocate an average density value for the different minerals that you have. Of course, you can change this value, and that will generate this density map here. So this would be a density map of the different minerals, and not taking into account the variation of density within each mineral. I have this density map, and the program will be able to find it. So then I can select this merge map, the fully calibrated data. And it works again the same way. I can add a region of interest to extract this local bulk composition. Here, I'm going to do it here, for example, in the center of the sample. And what you obtain on the right is this local bulk composition in oxide weight % for this domain. Again, you can change the shape of the region of interest. You can use a polygon if you prefer, or any shape you like. Also, what I included in this case is an option to calculate what would be an uncertainty on this local bulk composition. The idea is if each and every one of you would select a local bulk composition, you would have a slightly different values. So there is a Monte Carlo simulator inside here that will simply change randomly a bit the shape of this selection. And here you can change by plus minus 20 pixels for each corner. And if you click on that button, the program will change the shape or move the shape around also and calculate the different bulk composition. And this is the result. You see the whole black curve shows you a slightly different domain that was sampled. And the result is now reported here as the composition, the 2 standard deviation for each element, and the mean of all the domains that have been selected. So you can calculate an uncertainty that is related to this arbitrary selection of a domain to calculate this local bulk composition. And we have done quite a lot of testing because we are using bulk composition for modeling in metamorphism. And if you do an XRF bulk composition, you get to something very close to that number, provided that you select a large area and that you map a representative part of your sample. Again, you can change the domain here, and it will adjust automatically and recalculate your local bulk composition. You can, again, copy the data or save the data as a text file. I'm going to reset the region of interest here. There is one last option that I want to show you is for this part, is now from this merge map, what we can also do is we can come back to this classify button, we can select a mask file. Here, there is this plot button, and this will plot the composition. It will use the data of the merge map, and it will use the mask file to show you how is the distribution of each element between the different phases. So that will generate this plot automatically for you. So you know the main contributor for silica is, of course, quartz, and then we have plagioclase, garnet, and biotite. So this is a quite nice thing to do. You can easily generate this kind of plot. A last thing about the merge map, if you want, for example, to exclude a phase from this calculation of the local bulk composition, if I want, for example, to exclude the garnet, you can also merge your maps here, your quanti maps. You can simply select merge, and you can select the one you want to merge. And this will generate this merge map manual. And in this case, you excluded the pixels of garnet, and you can again use that to calculate a local bulk composition, now excluding garnet. So that would be the average composition of the matrix in my sample. I'm quickly showing you the capabilities in terms of structural formula and generating images. The first part is to calculate structural formula. It happens in the next workspace here, functions, where you have structural formulas for the main rock-forming minerals. If I pick here biotite and I select biotite as the quanti map, then I can simply apply the selected function and calculate a structural formula here for biotite. And now that will give me, for example, the XMG of my biotite. That's giving me the distribution of the XMG values in your sample. And you can immediately see the effect of the garnet of changing the XMG. There was re-equilibration of the biotite with the chloride. And this is something that you can visualize very nicely in this example. So you can calculate the structural formula for biotite. We could calculate the structural formula for garnet as well. The results are saved in this new category, results, below. And if I look at garnet, I would have this n-member fraction, X-almandine, X-13, pyrope, and grossular. I'm going to show you how we can generate what I call images. And those are images where you can save different elements and you can decide to save in the program the different settings of those images. So first, I'm going to save again the project. And I'm going to generate an image showing the maps of silicon, titanium, and XMG for my biotite. I want to have 3 maps together. And for this, you have to go to the menu. It's called Images, and you can activate this multi-selection mode. And the multi-selection mode is only used to create images. If I activate this option, then the tree turns into this blue, and now I can select several maps. I'm going to select silicon, titanium, and the XMG. And you see the program has now created an image with 3 maps. And I can go again to this image menu. The multi-selection mode is still active. And I can click add a multi-plot image. And this will generate a multi-plot image that is stored at the bottom in the last category that is called images. And you see that I have an object that is called this image multiplot number 1. And inside this object, I have a map of silicon, titanium, and XMG. But what is really nice is that now if you change the contrast, so if, for example, I adjust here silicon, then the titanium, I use the auto contrast for titanium, and the XMG, and I use the auto contrast. When I'm going to select my object, my image, now the 3 maps will be saved with the color contrast. So if you save your project and you come back a year later and you reopen this project, this image will still be available and you can come back and adjust the scales and keep this data set inside the program. It gives you an opportunity to save the figures that you want to save for later or that you want to show to someone when you are discussing this data set. The next part now will be to take the different plot and to generate different type of images. So I calculated here, for example, in the results, I calculated the structural formula for biotite, and I also calculated the structural formula just below for garnet. What is interesting here is that we can now create a new image that will combine the different data for the garnet and the biotite. To do that, what you need to do is select here one of the biotite, go back to image, reactivate this multi-selection mode, and for example, select the XMG in biotite, and then select here the XMG of garnet. And now what we have is XMG for biotite and XMG for garnet. And you have 2 options to combine them. Either you want to combine them using a shared scale, which means that you will have the same color and the maps will be overlapped, well, one with the other, or you can combine them using a multi-scale. And this is what I'm going to show you here. So I'm clicking combine with a multi-scale. And then you can go back to your object here where you have this map of XMG for biotite, XMG for garnet. You can adjust the contrast, let's say for the 2. And you can also change the color palette. If you go back to options at the top, you can select, for example, the blue for garnet and select reds for biotite. And now if I superpose those 2 images, what you see is the distribution of XMG values with 2 different color maps that shows you the relationship between the different minerals. And in the past, it was taking like hours to generate those kind of images by hand. And now you can straight away generate those images and save them in your project. I have a bit more examples that we have in the tutorial. If we want, for example, to generate an image of magnesium in biotite and garnet. And you see that when we calculate here, the structural formula, the program is using predefined maps. And for example, it gives you the amount of magnesium on the site M1, and it gives you the amount of magnesium on M2, but it's not giving you the total amount of magnesium in your biotite. This is quite annoying because if you want to display the number of atoms of magnesium for the structural formula, you cannot really have access to this map. So you will need to calculate another structural formula. What you can do in this case, you can generate the map directly from those maps. So you can select MGM1 and then go to module and use this generator module that allows you to create new maps from the maps that you have. You can create a new map that we will call magnesium equal magnesium on M1 plus magnesium on M2. So you can simply write your equation using the variable names that are available here in this table corresponding to each map. And the program will generate a new map here that is called magnesium. And that now is the sum of magnesium in your biotite. And I can reactivate my image multi-selection mode. And I go magnesium in biotite, magnesium in garnet. And I do image, add a multi-layer image with a shared scale. And now that will generate that image that shows you X magnesium in biotite. I can adjust the scale. And in garnet, oh, that's a bit hard for garnet, so I need to decrease a bit. And then I can go to biotite and change here. And now on my image, I would have on the shared scale for magnesium in atom per formula unit between biotite and garnet. And again, you can see the correlation. When you have grains at the contact between biotite and garnet, you see that they are enriched, the biotite is enriched in a magnesium. There are a few tools, especially for metamorphic petrologists. We have some thermo-barometry functions. I just want to show you an example from the biotite. In this type of rock, we can calculate temperature maps using titanium in biotite. There is the calibration that is coded in XMapTools. So you can select your biotite, go to thermo-barometry and other methods, select map mode, biotite, press apply, and this will simply calculate the temperature. You have to fix the pressure. And now in the results, I will have a new result that is biotite thermometer. And this is the calibration of Henry et al. 2005. That would be the calibration of Wu. And so you can display the temperature map. And here you see the temperature is ranging between 740 degrees and about 660 degrees. And that shows you that with condition, the biotite was recalibrated. I'm going to show you an example. If I go to the structural formula of garnet and I look at the amount of pyrope, so this is the amount of magnesium in garnet, and you see that I have this zoning here in the garnet. If you want to extract, for example, to do diffusion modeling studies, a transect between the core and the rim of your garnet, you can use for that the sampling tools. So you select the map you want to plot, you adjust the contrast, and then you can use the sampling tools. And let's do a transect in this case and go between the outside of the garnet toward the core and do it like this. And now you see that I have created a transect from the point number 1 to point number 2. And this is how the profile looks like. And the color corresponds to the color of the pixel. You can decide to adjust this if you want. We could do a slightly more complicated transect going, for example, here to the core and then toward the rim again in another direction. That will give you your new transect here. And this is really nice because you can adjust always the position to find the right position that would look better on your transect. This is especially convenient when you want to do some diffusion modeling. But at the beginning of my talk, I told you that we can do more precise than spot analysis. And here we are clearly not as precise as spot analysis because on each pixel, we have only 100 milliseconds of counting time. So I was telling you we should integrate pixels together. And to do that, one of the options is to use a sampling stripe. And what you can do is to create this rectangular area. And then the program will integrate. I'm rotating the area here in the garnet. And it will simply integrate all the parallel transects in this area and give you the median in red and the mean in blue. Now what you get is something that is smoother than before. And that's where you can start to reach a precision that will be better than your spot analysis. The diagram on the bottom here shows you all the transects of this strip here. You can decide to export the data. You go to save result. You can save the result for a single map, or you can save the result for multiple maps for the same transect. Let's do it, for example, for all the garnet end members, and it will be in exported sampling. That is the one we just did, and now it's saving the data. And if you open the text file, you will have all the data here that is saved. Of course, if there is nothing, this is the black pixels, it will be not a number. And then those will be the data for each element here of the file you selected. And then it will export the distance here in micrometer and the different values. And you have also a backup of the map. So it automatically will save the image, showing you where was the sampling. And you have this figure with all the data along that stripe that was automatically saved. You can also use the other one. For example, if you want a circle and you want to know the composition here in this circle. So if I select pixels, then the green line here will show you the average value. And here you will read the average value plus minus the standard deviation of the pixels within that region. And this is simply an histogram of this plot. The last thing I want to show you is how to do this pass between the data, the map data, the plot, the chemical plot, and to come back to the map data. And for this, I'm going to use this module that is called data visualization module. So we're going to start with simply selecting a biotite result in structural formula. Then we're going to go here to module, data visualization. And it will open this data visualization module. And you can select between an histogram of one of the elements of your structural formula of biotite, or a binary diagram, or you can plot an RGB image, or you can plot a ternary diagram. But let's focus here on the binary diagram, and I'm going to plot XMG versus titanium in M2 site. And this is the plot of all pixels. And again, you can see that we have probably some points here that could be mixing between the biotite and the titanium-rich phase, such as rutile or ilmenite. And we can use, again, this auto contrast to zoom on this, so to exclude some points and zoom on this area, or we can simply click zoom here and select the range of data that we want to display to adjust this plot. And we have this cloud of pixels. We can also, if we inactivate this low resources mode, the program will get a bit slower, but it will also generate a density plot, a density map. I can readjust the contrast here. And now I get also the density image. In the previous case, with the low resources mode, I was plotting only part of the data, and now we are plotting 100% of the data. That's what makes the software a bit slower in this example. So maybe we don't need here the low, we just don't need it. We just focus on the low resources mode, and we focus on this area. If we want now to know where are the pixels located in the map, we can go to Explore, and we can click polygon, and then we can select simply a domain on that plot, and it will plot all the selected pixels. Yeah, here it goes. All the selected pixels for biotite will now be plotted in red on that figure, and you can modify your polygon, you can move it around, and it will update the plot here on that figure. So this really allows you to explore where are located some pixels with a specific composition you would be interested in. For example, where are they located in IMAP? So this is the tool that you can use to go from the map to the compositional diagram back to the map. And you can even say, oh, I'm very interested by this region and I want to save it as a mask file, and you can make a mask that will save a mask file that you can import in XMapTools. And so you could look at only the data of this particular selection of pixels. If you want to export an average composition, for example, that would be possible. You can do that in the binary plot, but you could also do that in the ternary plot as well. So you could do exactly the same thing, select the domain and where are those pixels distributed on the map. And the last thing I want to show you is really to look at the intensity data with this module. And if we go back to the intensity maps and we reopen that module, and I was talking before about the mixing pixels. And this is how we can really identify the mixing pixels that we have in our map. So we can go back to the binary module, aluminum and magnesium. And you see that each group of dots here corresponds to one mineral. So we could use the polygon here to identify the minerals. And we could create a classification like this. This is a manual classification, but you could select that mineral, say, okay, this is my chloride, and you could create mask file, and then you could import those mask file in XMapTools as a classification. So you could do the classification yourself. But here, what I want to show you is that between the different groups of the minerals, you have those lines, and those lines are the mixing pixels. And you see that it's pretty nice because it goes really between the different groups. So by selecting, for example, the pixels here, you will get all the mixing pixels between this mineral that is rich in magnesium, that would be the biotite, and this mineral that is probably quartz. And those are the pixels with a mixing composition between biotite and quartz.